Hi, we're going to go through a PowerPoint presentation today. This is a case study that I did on how some manufacturers use induction in their diagnostic strategies for their computers or their ECUs. So what I want to do is explain a little bit of what induction is, why it's useful in diagnostics, and then we're going to go over a case study demonstrating how it's useful in diagnostics. So let's just get after it. So the inductive voltage kick, explained quickly and incompletely. Inductors create a magnetic field by resisting current flow until complete saturation. The inductors also resist change in current flow when it's interrupted. So when the current flow is interrupted, the inductor uses the energy stored in the magnetic field to attempt to maintain current flow. The potential energy of the magnetic field as it attempts to maintain current flow is measured in voltage, and it shows up as an inductive voltage kick when the current flow is interrupted when an inductor is fully saturated. So we're going to dive a little deeper into this. So a solenoid is an inductor that does work using a magnetic field as it generates. So basically you can think of an inductor as an electromagnet. It uses electricity to create an electromagnetic field, so that field is what creates the voltage when it collapses. So if the current cannot flow, the voltage will rise. So when that current is interrupted, all that potential energy that's stored in that magnetic field has to go somewhere. Or wants to go somewhere. And if it's completely stopped and is still attempting to flow, it's going to cause a quick rise in voltage. This effect can be seen on an oscilloscope as an inductive kick as the solenoid is switched off. And you can see that in the lower left-hand corner. Over here, you can see this is a fuel injector. It's on here. As it's switched off, this is the control or the ground side of the fuel injector. When that's switched off, you can see we have over 120 volts on that circuit when it's switched off. That is the energy in the magnetic field attempting to maintain current flow. And since it can't maintain current flow, the voltage has a sharp increase. And you can see that represented there. And then you can see as the energy wanes off, because it's not unlimited energy, but it's going to use up as much of that energy as it can trying to maintain current flow. And you can see as the energy wanes away, you can see that voltage drop. And that's where you can see the voltage dropping here over time. And it all happens relatively quickly. This is a 2 millisecond window, so it happens very, very fast. But it does happen, and it's important that we understand that because that's useful. And here's this lower right-hand corner is an example of just a simple solenoid moving a plunger. It uses electromotive force in the magnetic field to pull this plunger when it's activated. And then when the magnetic field collapses as current flow is shut off to the solenoid, the plunger gets released. And as that field collapses, the current has nowhere to go, so it creates a voltage spike. This is important to understand. In modern electronics, they're starting to use this effect to their benefit using computer analysis to determine faulty components or faulty circuits. So this is really important to understand and make sure this makes sense to you. So now we're going to get a little deeper. We're looking at electromotive force, suppression, and voltage clipping. So high voltage can be extremely dangerous to sensitive computer components. And there has to be a way to deal with that. So this is how we're dealing with it. This is how this gets dealt with in several different ways. So chances, there's typically a resistor or a Zener diode that controls the current. And you can see that in this upper right-hand corner. The flyback diode and the resistor helps maintain current flow so that energy gets used up and keeps the voltage low. So, and then you can actually see the effect of this circuit on an oscilloscope, because if you're seeing a solenoid or an inductor switched off and you're not seeing the inductive kick, it's being managed in some way. And typically it's through like a Zener diode, a flyback diode they call them, or a flyback circuit using a resistor and a diode in this case. So it effectively, they can reduce that flyback voltage to a safe limit or even a usable limit. The voltage clipping circuit takes things to another level and makes it even a little bit more complicated. So instead of just regulating it to, say, 12 volts and not allowing the voltage to go over 12 volts when you shut that off, they may regulate it at a specific voltage. So, and there'll be some I'll have some scope captures here to kind of go over that. But it is important to understand when using an oscilloscope to capture and analyze waveforms that you understand what's happening in that circuit. I know this isn't fun, but it is really necessary to understand this. And you can see the various examples of how this is dealt with. The old points ignition, they actually had a condenser or a capacitor in line to absorb some of that high voltage. And why that was necessary is because it would actually burn your breaker points if the voltage was too high when you were breaking that circuit. That's an ignition coil, which is also a inductor. It's also a form of a solenoid. It's not physically moving anything, but it is creating a magnetic field, and then the collapse of that magnetic field actually creates a spark on the secondary ignition windings. In much the same way, where if you monitor the ground side or the control side of an ignition coil, you'll see a very, very high inductive kick, because that inductor, again, is still trying to maintain current and can't because the circuit goes open, so it's going to drive that voltage very high. The following case study demonstrates how the manufacturer takes advantage of EMF for diagnostic purposes, and how you can too. It's extremely useful once you understand the basics of this. The following examples we'll go over, where this is a pulse width modulated circuit, and you can see the voltage never really rises above, say, 13.6, 13.8. And if there wasn't EMF management in this circuit, you would see the inductive kicks every single time that solenoid is cycled off. And you can see they manage it really well here. And here you can see the solenoid shut off, and you can see there is a slight rise in voltage, and then kind of a tabletop here and here. This tabletop is actually the voltage being managed. This voltage actually creates a peak and a downward wane as the voltage wanes off. But you can see here that peak is clipped off, so there is some EMF management going on inside this ECU controlling that, maintaining a safe level. And you can see that doesn't really peak much over, say, 50 volts. So it's important to understand what we're looking at here. And here's another example. You can see the clipping here at the beginning of this circuit as it starts. More than likely, this is a capacitor being charged and then maintaining that voltage at 12.52. But at the beginning, you can see it just struggles as the capacitor starts to become charged. It just struggles to maintain that, and then it can maintain that voltage. So you can see that circuit doing work there. And here you can see an unmanaged EMF where it's a nice sharp spike all the way up, very high voltage. We're almost 100 volts and almost 95 volts. So a very high inductive kick here, no management, just a nice sharp peak and back down as that voltage wanes away as the magnetic field collapses. And again, here zoomed in, no management, nice peak at the top, real sharp, just straight up, straight down. This was meant to be a live demonstration. If you have any questions, feel free to leave them in the comments. I'm always happy to answer questions as long as I have time. So I typically will follow up if you ask a question. I do want to make sure that if you're watching this, watch this first section a few times if you need to do some research on your own. I'm definitely not an expert in inductors and all the nuances of EMF management. But it is important to understand that has to be managed and the different ways that it is managed. So now that we understand how inductors work, how they resist change in current, and how when a saturated inductor is flowing current through it and you interrupt the flow of current, it's going to want to maintain current. So you are going to have a high voltage situation if you interrupt the current flow in a circuit that has an inductor in it, if it's not managed in some way. All right, let's go diagnose a truck. Today's problem vehicle is a 2018 Ram 2500 HD 6.7 liter diesel automatic transmission. It's got the 6.8 RFE in it. The transmission will randomly stop shifting correctly. The vehicle has a remanufactured transmission. It's on its third remanufactured transmission in 500 miles. A reman company needs to know the failure cause and confirmation before servicing the warranty. They've already warrantied it a few times, so they really want to know what is going on. So that's how it ended up at my shop. So the first look, we checked it over. The fluid is clean and full. No DTCs stored in the PCM. The customer did drive it over. He cleared the codes a few times bringing it over. We're going to go down a weird rabbit hole here really quickly and then move on. This is a 2018 truck. It should have a secure gateway. How did the customer clear the codes? So I grabbed a scanner that has gateway access, couldn't communicate with the gateway. The tool failed to authenticate, and I proceeded anyway. Everything works. It acts as if the gateway doesn't exist. Realized the truck has emissions deletes on it. After doing a little bit of searching on Google, I found they do make a gateway bypass module for these trucks, and they're pretty cheap. So the gateway... it's safe to assume there's a gateway bypass module. I don't really care because it doesn't matter for this diagnosis. It's behind the radio. I'm not going to pull the radio to find out. I have a scanner that works with it. I'm going to move on. But, this is just one of the many variables we deal with when diagnosing a vehicle, that you never really know what it has on it for aftermarket parts and accessories. And sometimes it's a problem. Sometimes it's no big deal. So it's important if you're diagnosing cars every day to understand the potential for aftermarket devices to cause more headaches and trouble in your diagnostic process. But decisions made. It's not going to affect my diagnosing at all of the shifting concerns, so I'm going to move on. Excuse me. No failure on the first test drive. Took it for a 20-minute test drive. It was warmed up when the customer dropped it off. They showed up on time for their appointment, so we basically hopped right in it and took off. The vehicle was allowed to cool to ambient temp after the test drive with no symptoms. On the second test drive, a single DTC set multiple times on warm-up. Once the vehicle reached operating temperature, the DTC would not return if cleared. The DTC in question is the P0770 770. It's a 4C solenoid circuit. The continuity of each solenoid circuit is periodically tested using the ECU. So this is the description in the service information. Each inactive solenoid is turned on for a few milliseconds and then off. Each active solenoid is turned off for a few milliseconds and then on. This pulsing of voltage to the solenoid causes an inductive spike, which we discussed before, so you know what that is, which can be sensed by the transmission control system. If an inductive spike is not sensed by the transmission control system during the continuity check, which is what they described there in the beginning, it is tested again. If the test fails 3 consecutive times, the appropriate DTC is set. If the solenoid test is run in response to a gear ratio pressure switch error, one failure will result in setting the appropriate DTC. So this is just more of a breakdown in the service information that covers this code. So again, after 3 consecutive solenoid continuity test failures, or one failure if the test is run in response to a gear ratio or pressure switch error. This DTC is strictly an electrical fault. It's nice when they put a note in here like this, because we know we're probably not dealing with an internal transmission failure. We're not dealing with a clutch. We're not dealing with a stuck valve or something like that. We know how it monitors this circuit to set this code. We know it's looking at the inductive kick, and it's monitoring the solenoid circuit for an issue. So we know chances are it's not going to be a clutch, it's not going to be a stuck valve, it's not going to be contaminated fluid, it's not going to be a bad torque converter. We know that it is a circuit issue. Now we just have to figure out what's going on. So we know that it uses the inductive kick to test it, which is really, really useful. So let's go through more of the diagnostic process in the service manual. It gives us our possible causes. The 4C solenoid control circuit shorted to other circuits, the 4C solenoid control circuit's open, or the 4C control circuit is shorted to ground. That's it. That's all it says for our possible causes. It could also be the TRS assembly, which is all the solenoids in one assembly, or the PCM. So we know it's basically like any other circuit issue. We're dealing with either a circuit problem, a faulty component, or a faulty controller, which basically gives us no information, right? We know it's one of the 3 things, which is, it's pretty obvious. So as we go through the troubleshooting procedure, it says check for DTCs. We do have a DTC. We looked at the procedure. On to number 2, check the 4C solenoid using the transmission simulator. So, I don't have a transmission simulator. It looks expensive. I'm probably not going to buy one, and I don't want to ship this vehicle to somebody that has one. So, what are we going to do? It's not a big deal, right? Because we know how the ECU determines the fault. We can test it in the same way as the PCM does. Let's look at the inductive spike the PCM uses for diagnostic purposes. Here's the theory of operation. The transmission control system uses 5 electronically controlled solenoids that allow hydraulic fluid to be applied to various friction elements, the clutches, which enables the gear requested. The continuity of each solenoid circuit is periodically tested. Each inactive solenoid is turned on for a few milliseconds, then off. Each active solenoid is turned off for a few milliseconds, then on. This pulsing of voltage causes an inductive spike, which can be sensed by the transmission control system. If an inductive spike is not sensed by the transmission control system during the continuity check, it is tested again. If it fails more than 3 consecutive times, the appropriate DTC is set. If the solenoid test is run in response to a gear ratio, we already know all that. So we know how it works. And we're looking at that inductive spike. So the easiest place to test this, and again, I'm huge on non-invasive testing. I always want to do the least amount of work with the most amount of information gathered. So in this case, the easiest place to test, the most convenient, is at the TRS connector, which is on the side of the transmission. So that's where we went. We have the 4C control here at 19. We're going to go ahead and back probe that and then put our ground clip on ground and see what that looks like. And here, the red trace is the 2C solenoid control, and the blue trace is 4C. And we're assuming these two solenoids should make the same inductive spike. They're basically the same solenoid, so they should look the same. Here we can see they're different. Now, I'm not super confident that that is enough to condemn a solenoid. Not yet anyway, but let's keep going. So the red is the 2C solenoid, blue is the 4C solenoid. The key on diagnostic pulse is what you saw in that last slide. The high pulse width modulation there, where it gets really fast, is scanner control. So you can see the inductive kicks both at the same voltage level on either one. So all that looks okay. The circuit appears to be operating normal. This is an intermittent issue. I suspect a solenoid problem based on reoccurrence during temperature changes, and the fact that once it was warmed up, it didn't act up. But as the fluid was getting warmer, it acted up multiple times. So this could be very difficult to prove, but let's take a closer look at what we have and see if we can pinpoint a problem. So we can see the voltage is limited to about 42 volts. And we can actually measure the time that the voltage is being clipped, which is about a half a millisecond. And you can see here, each one of these squares is 1 millisecond. So if you were to slide this over, you can see it takes up about half a square. So that's about half a millisecond across the top of here. And that tells me that the voltage being clipped is going way high, way above here, and then coming down a nice even slope. So I can judge, based on the time that the voltage is being clipped, how high this spike could potentially be. We could actually figure it out with a bunch of math, but I'm not going to do that. But I could tell you that the voltage is going to be higher on this than one that has half this amount of clipping, because it takes time for the voltage to go high and then come back down. I want to make sure that makes sense, because that's how we're going to determine we have a problem. Here you can see the voltage still is limited at 42 volts, but the time being clipped is 0.1 milliseconds. You can see we're zoomed in here. So 1 square here is actually 0.2 milliseconds. And again, this is actually probably a little less. But if we were to put this in here, it's probably about, well, less than half. So less than 0.1 milliseconds. We have one little weird spot there. And that could be, anybody that's used to using a scope, that could be a little glitch, could have bumped something, who knows, right? Here the voltage is also limited. The time being clipped is less than 0.1 milliseconds. And we still have a weird spot, roughly the same spot too. Just a real little spot. Well, you can see that since this is more narrow, it's safe to assume that the high peak of this voltage is lower than the 2C solenoid, which was the red trace, that was almost 5 times wider. So it's safe to assume if the amount of time that the voltage is clipped is 5 times longer, that the voltage may be up to 5 times higher at the peak than it is on this one. That's a pretty significant difference. That's enough to cause concern. and so is that. So you can see we zoomed in, we're still pretty zoomed in here. We're still at about 0.2 milliseconds per square. And that is quite the problem. So what that's showing there is an open in this circuit. And you can see that as the voltage disappears and comes back. So you can see there's an issue here with the energy flowing. So what would cause a disruption as the current is flowing, or attempting to flow, as the voltage is waning out of this solenoid? What is going on here? That has to be a break in the windings. That's about all it can be, is a break in the solenoid windings. So, can we confidently call a faulty solenoid based on our measurements? I think we can. So we did. We swapped out the solenoids. The blue is the original. This is on that diagnostic pulse key on engine off. And you can see the blue is the original. The yellow is the new solenoid. And the yellow one, key on engine off, that voltage clipping is around 0.7 of a millisecond. So we know that the problem is that when that solenoid was switched off, the amount of inductive kick, or the amount of voltage created by the inductive kick, was significantly less than the new solenoid or the 2C solenoid. And that's how we got to the bottom of this. We didn't have to do a bunch of extensive testing. We didn't have to waste a bunch of time. We were able to go through this methodically and logically and make sense of what's going on without having to have a special tester and without having to guess. And I don't think this could be diagnosed properly any other way without an oscilloscope, without understanding how this works. And here is the diagnostic key on engine off test with the 2C and the 4C next to each other. We can see they're pretty much identical. So the assumption that both solenoids would have a similar inductive kick based on the diagnostic strategy of the PCM software was accurate. Therefore, this fault can be proven key on engine off test in the bay. So if you have these codes, or a code relating to these solenoids in this style truck, it wouldn't hurt to go ahead and back probe all the solenoid controls, turn the key on, get a picture of them, and see if any of them are creating a lower inductive kick than the rest. I would feel very confident condemning a solenoid using this test alone, especially after going through this step by step by step. I'd feel absolutely certain that if I had two similar solenoids and one is creating a 5 times less inductive kick than the other, I'm going to condemn that solenoid. Thanks for watching. I hope you learned something. I hope this all makes sense. This last one's another really nasty shot of that failed one. You can see the disturbance in this inductive kick is either going to be movement of something ferrous or something that's going to disturb this magnetic field, or it's going to be a problem in the windings, whether it's a break or a short. You're going to see it in that inductive kick more than likely. So if you have any questions, please leave it in the comments. I appreciate you watching. If you like this, please share. I know these case studies aren't always the most exciting thing in the world, but there's a lot of good knowledge here, a very, very useful technique. So I hope this helps you out, and enjoy, get out there and fix some stuff. Thanks for watching.